Hi, this is Sudeep, and I welcome you back to this wonderful journey of learning structure analysis with STAAD.Pro. In this session today, we will start the actual analysis of structure. So far, we had spoken about how we could model the structure in STAAD.Pro, and we have discussed all the associated theories along with that. But in this session, as I've said, we will start the actual analysis. Our plan today is like this, that we will first calculate the reactions of a given structure, which is statically determinate, and then we will model that same structure in STAAD.Pro, obtain the reaction results in STAAD.Pro, and compare that with our manual calculated reaction results. We will also check the stability results from the statics check table. But before we go forward, please do take a moment to hit the subscribe button and join us in this wonderful journey of learning structure analysis with STAAD.Pro. So this is the structure that we are going to analyze today. This problem has been taken from the famous book Elementary Structure Analysis by Charles H. Norris, John B. Wilbur, and Senaloicu. Now, as we can see, this is a pinned rollered beam where the beam has been created between nodes 1 and node 2. The left node, node number 1, is pin supported, and the right node, node number 2, is roller supported. The beam spans for 18 feet, and for the loading, a 60 kip load is applied vertically downwards at 6 feet distance from the start node, and then there is an inclined load which has been inclined in a slope of 4/3 at a distance of 6 feet from the end node 2. Now we will consider the global axis system in such a way that node number 1 lies at the global axis origin. The blue axis here represents the global x-axis, and the red axis represents the global y-axis. Now, we could remove the pin support and replace it by the restraints that it would provide, which would be a vertical reaction and a horizontal reaction. Now, we have considered both this reaction along the positive direction of the global x-axis. This is an assumption, and our calculation would verify whether this assumption is true or not. R1V means the vertical reaction at node number 1. R1H means the horizontal reaction at node number 1. Similarly, we can remove the roller support and replace it by the restraining force that it provides, and thus we have the vertical reaction R2V, which means the vertical reaction at node number 2. Now, for easier understanding and a clear view, we have considered or shifted the global axis representation at the left bottom corner. This does not mean that the global origin has been shifted. The global origin is in its place, but we have represented the global axis just as a representation to help us remember the directions along the global x-axis. Now, this representation of the structure that we see on the screen, where the support representation has been removed and has been replaced with the restraining force that those supports provide, is called a free body diagram. A free body diagram is a representation of the whole structure or the part of a structure where it is only represented with its applied loads and the reactive loads on it. So free body diagram is a very important concept which we will use consistently as we go along. Now, let us consider the inclined load be inclined at an angle theta. Now, we already know that the load of 60 kips is inclined at a slope of 4:3. That would mean that the angle theta would be calculated as tan inverse of 4 by 3, which would be 53.13 degrees. So this inclined force of 60 kips will have a horizontal component of 60 cos theta, or 60 cos 53.13 degree, which would be 36 kips. There would be a negative sign before it because the way this load of 60 kips is inclined, the horizontal component would be acting along the negative direction of the global x-axis. Now to calculate the vertical component, it would be 60 into sine of theta, which would be calculated as 48 kips. Now again, there would be a negative sign before it because the vertical component of the 60 kip inclined load would be acting along the negative direction of the global y-axis. So we can now represent the inclined load as its equivalent vertical load of 48 kips and the horizontal load of 36 kips. Now let us calculate the reactions of this pin roller beam. As you may remember, this is a statically determinate system, so we can use the equations of equilibrium to solve for the reactions. So before starting, let us quickly have a relook at the reactions, and we have assumed that all the reaction forces are aligned along the positive direction of the global x and the global y axis. So let us use the first condition, or the first equilibrium condition, which is sigma fx equal to 0, which means that the summation of all the forces acting along the global x directions is or will be equal to 0. So what are the forces that are acting along the global x directions? Well, the first reaction is R1H, which is the horizontal reaction at node 1. We are giving it a positive value because we have assumed it to be positive along the global x-axis. The other global x-axis force is 36 kips, but this has a negative value because it is acting along the negative direction of the global x-axis. If we sum that up, it would be equal to 0, which would mean that the value of R1H is equal to 36 kips. This means that the assumed direction of the horizontal reaction is correct, and that is why we get a positive value for it. If we had got a negative value for R1H, it would mean that the force would be in the opposite direction than we have assumed, but no such conditions exist here. R1H has been assumed correctly, and thus we have got the load value, or the reaction value rather, as 36 kips. The next equilibrium equation that we want to apply is summation of mz1 is equal to 0. So remember that the global x and global y axis are actually located at node number 1 being the global axis origin. This also means that the global z-axis is coming out from node 1 out of the page towards you. So if we take the summation of the moments of all the force about the global z-axis at node 1, that has to be equal to 0, and this is what is represented by this equation. So let us take the moments. The first moment that would be created about node number 1, about the global z-axis, would be by the reaction value R2V. Now here we have assumed that R2V is acting along the positive direction of the global y-axis. So as per the right hand thumb rule, if your thumb points towards the global z-axis, the moment that would be created by R2V about that point would be anti-clockwise, which would be represented by the curl of your finger if you're using the right hand thumb rule. If you have confusion about right hand thumb rule, you can refer to the session that is appearing on the top right of the screen right now. The next moment is the vertical load of 60 kips, which is acting at a distance of 6 feet from node number 1. So the moment would be 60 into 6 feet. Now, it would be negative because it would be the moment that would be created by the 60 kips located at a 6 feet distance would be in the opposite direction than the curl of the fingers that would be created by the right hand thumb rule, or rather it would rotate in the anti-clockwise direction. Remember that when you are using the right hand thumb rule, the right hand thumb would point towards you, that is along the global z-axis, as the global z-axis is pointing towards you. The next moment would be from the vertical load of 48 kips, and it is located at a distance of 12 feet from node 1. Even in this case, the moment would be clockwise, so we have a negative value to it. And the summation of all these moments created by these forces would be 0. Now, you may ask that what about the moments by the 36 kip force, the R1H force of 36 kip, and the vertical reaction at node number 1. What about the moments due to these forces? You would notice that all of these forces that hasn't figured in this equation is passing through node number 1. So the distance of those forces from that node number 1 is 0, and thus there won't be any moment due to these forces. So that's why we haven't considered those forces. Now, if we solve the equation so obtained, we will get R2V, which is the vertical reaction at node 2, as 52 kips, which would again mean that the assumed direction of it being acting along the positive direction of the global y-axis is correct. Now we will use the last equilibrium equation, which would be summation of Fy would be 0. So sum of the forces along y would be 0. And what are the forces that are acting along the global y direction? Well, the first one is R1V, the vertical reaction at node number 1. The second one is R2V, which is the 52 kips reaction that is acting at node number 2. Now, 52 kips would be positive because it's acting along the positive direction of the global y-axis. Then 60 kips, which is the applied load at 6 feet distance from the start node. Now, the value would be negative because it's acting along the negative direction of the global y-axis, and similarly we'll have minus 48 kips. If we sum that up, it would be 0, and this would mean that R1V equal to 56 kips. Again, R1V equal to 56 kip would mean that the assumed direction of acting of R1V, which is along the positive direction of the global y-axis, is correct. So with this, we have solved for all the reactions of this beam, where the horizontal reaction at node number 1 is 36 kips, the vertical reaction at node number 1 is 56 kips, and the vertical reaction at node number 2 is 52 kips. Now that we have analyzed the beam manually, we would want to analyze this beam in STAAD.Pro. For that, we would need to model the beam in STAAD.Pro in the first place and then analyze this particular beam. Once we analyze this beam in STAAD.Pro, we would see what is the reaction results in STAAD.Pro, and we'll compare those reaction results with our manual calculations. But before we go doing that, we have to configure the base units. Now that our units of these structures are in kips and feet, we would need to ensure that the base unit settings is set to English. Now, why do we need to do that? Well, to understand that, you need to refer the session that is appearing on the screen right now, where I have discussed this in details. So once I have set the base unit settings to English, I click on OK and click on the new structure, and we'll say that we want to define a beam pinned roller calculating reactions, and we say we would select the location, an appropriate location where we want to save this beam, we say that we save that in the D drive, and we ensure that the units are set in English. We say create. Now, as soon as we get into STAAD.Pro, we need to go at the top bottom corner, and we'll see that the input units are in keep and inch, but we have a different requirement. Our input unit system should be in keep and fits and not keep and inch. So what we'll do is we'll go on the top ribbon, and in here you would see this icon here which says input units. So we click on this and ensure that the length unit is set to foot. The force unit is set to kilopound, which is okay. And we click on apply. We see that the input node table still shows the units as inches, where we have already changed that to fit. Now this is just a refreshing issue, so just go to properties and come back to geometry, and you will see that it has been updated to fit. Now remember that our node number 1 was at the global origin, so we defined the node coordinates at 0, 0, 0. Our node number 2, remember that the span of the beam was 18 feet, so we say 18, 0, 0. And we say that our beam has been created between node 1 and node 2. Now that we have created this beam, remember that we had 2 point loads that has been applied on the beam, one at a 6 feet distance and the other point load, which was inclined, was applied at 12 feet distance from the start of the beam. So basically the beam has been divided into 3 equal parts by insertion of 2 nodes here. So we have to then select this beam and click on the insert node from this ribbon menus. So click on the insert node option, and we say that we want to divide this beam into, or we want to add 2 additional points which would divide the beam into 3 equal parts. So we say add endpoints, and you can see in the representation here that the beam would now divide, and the beam would now be divided into 3 parts, and we say OK. And we will see that using the dimensioning tool, we'll see that the first point load application will be at this node, which is at a 6 feet distance, and the second point load, which is inclined, would be applied at a distance of 12 feet from the start node, which is what we had wanted. So we remove the dimensions now. For properties, we can't define anything here. It doesn't matter. So we'll define this as maybe the depth of that beam as 16 feet and the width of that beam as 10 feet. We click on add and we say assign to view like this, and then we will have also assigned the material concrete along with it. Now let us go and assign the supports. So, but before that, let us change the view to the front view so that we can see the view in the XY plane. So now let us create a pin support which needs to be assigned. Just switch on the nodes, and the pin support needs to be assigned to the leftmost node. And then we want to define a roller support by defining fixed butt releasing in FX and MZ direction. We click on the support tree representative of the roller support, and we assign it to the rightmost end of the rightmost node. So if we switch on the node numbers, the pin support has been assigned to node number 1 and the roller support has been assigned to node number 2. Now the node has been defined. Now we want to define the loading. So we want to go to the load case details, and we want to add a primary load case. So we say load case number 1, where we'll define both the point loads. We say add yes, and we click on this load case number, go to the nodal load, And remember, the first node was a 60 kip node that was acting along the negative direction of the global y, so minus 60 kip, and we add it to the load case. So it has been added to the load case here. Then there was another load of 60 kips, which was an inclined load. So we'll say that we want to define it as an inclined load, and such that the new x-axis would be pointing towards a point which is located at a coordinate of 16 feet below the first node, or node number 1. How I have calculated the 16 feet below node number 1 is something that you can refer to the session that is appearing on the screen right now, where I had discussed on how you want to create the inclined loads. So we now can define this load as 60 kips inclined load, and we say add. So we assign the first load here, which is 60 kips. So we want to adjust the scale a bit. So we can always right click, go to labels, select the scale, and increase the value here to make the load view smaller. Let us say apply immediately. And so yeah, maybe this is the right size. And we say, or maybe a bit bigger. So we make the number smaller to make it bigger. We say apply and OK. And then we assign the inclined load at node number 4. I think there has been a mistake in the way that we have assigned the load. So let us go there. And we want to assign that along, I have, sorry, it would be plus 60, but the coordinate here would be minus, because it is located below node number 1, so it would be minus. So now if I modify the load, you can see that the load is being applied in the right direction. Now once I have done this, I need to add the analysis command. Again, I had discussed in details on the perform analysis command, and in order to view that session, please click on the link that is appearing on the screen right now, and where you would learn about the opportunities and limitations of using the perform analysis command. Now once this is done, we'll uh, click on the analysis and add the perform analysis command. Once we have done this, we want to go into the input file, and we will see that we have defined the whole structure. The unit has been defined in feet and kip as we had wanted, defined the coordinates, defined the member incidences, defined the section, and we have defined the material, we have defined the supports, we have defined the loads, and then we have given the perform analysis command. Now that we have done this, we can hit the run analysis button and run the analysis to complete this analysis. If you have any questions, please do ask them in the comment section below. If you have liked this session, please do hit the like button, and please join us in the forthcoming session. Till then, bye bye.